We're going to learn about stars today and how they die, I think usually from overdose. Alright, stars, next generation chemistry, let's go. The energy produced by stars is solar fusion. It's the fusing of two or more lighter nuclei into a larger one. Hydrogen, which is one proton, combines to form helium, which is two protons. This is called fusion, smaller things making something larger. Helium will then combine to form larger atoms, so heliums will combine. And over the life of a star, it will build up to larger and larger atoms. This process, as nuclear fusion, releases a lot of heat and energy. Nuclear fusion is in the sun's core. A tremendous amount of heat and pressure is put on these nuclei, and that pushes them together, or fuses them together, which gives you this massive amount of energy. The heat and energy travels outward from the core, creating magnetic fields. So as this heat and energy travels out from the core, it creates magnetic fields. The motion of energy creates magnetic fields. Solar flares are bursts of high energy electromagnetic waves. The magnetic fields that originate from the core burst out through the surface of a star or the sun, and when these magnetic fields reconnect, it creates a solar flare. This electromagnetic waves shoot out in all directions from this area. Solar flares are big, bright flashes on stars. Solar flares are often associated with active magnetic regions, which are called sunspots. These sunspots are cooler than the area around them, and they appear dark on the sun. They are enormous, though. These magnetic fields are huge. In fact, you can fit Earth in some of these larger sunspots. But solar flares are not the only thing that's coming off of a star. Coronal mass ejections, or CMEs, are giant clouds of particles hurled into space, mostly made up of protons and alpha particles. And as you can see, they can go quite far throughout our solar system. Coronal mass ejections and solar flares are sometimes occurring together. However, it's important to note that they are two different things. This bright flash is the flare. The flare is releasing electromagnetic waves, primarily X-rays, where a coronal mass ejection is actual matter, protons and alpha particles. Sunspots reappear regularly on a cycle of about 11 years. So every 11 years, you'll have times when there's virtually no sunspots visible on the sun, and then it'll peak at, in some cases, it looks like here in the 1960s, we had over 250 sunspots that were observable, and then it drops down to almost nothing again. So every 11 years, we see this cycle of a lot of sunspots to not so many sunspots. Remember, sunspots are activity of solar flares, which commonly occur with coronal mass ejections. So having said that, what effect does solar activity have on the sun's energy output? In other words, when there's more sunspots, that's more solar activity. What does that mean with the sun's energy output? Is it producing more energy or less energy in the presence of more sunspots? Pause the video and answer that question. Okay, let's talk about the next thing, solar wind. Solar flares and coronal mass ejections from the sun are referred to as solar wind or space weather. So as the sun is releasing electromagnetic waves, as it's releasing coronal mass ejections, alpha particles, and protons, this disturbance in space, this release, is called solar wind or space weather. Solar wind can disrupt and damage electronics in space or on Earth, so satellites have to be shielded and protected from this. Aluminum seems to be a good source of protection, but a direct large solar wind that would hit a satellite would completely knock it out. Solar winds can move up to 0.87 million miles an hour, or 1.4 million kilometers an hour. So these things are moving extremely fast in space. Earth has a magnetic field around it, and this magnetic field helps protect Earth from the solar winds or the space weather. So Earth's high-speed rotation and molten core create a magnetic field. Because we've got an iron core and it's moving very fast, remember, energy moving creates a magnetic field, and it moves on this axis, so Earth has a magnetic field that comes from the poles of Earth. And that's how compasses are used, because we've got these magnetic poles, and so a compass will point you to the North Pole if that's what you're looking for. Okay, so Earth's magnetic field blocks solar wind. So these yellow lines are going to represent solar wind, and these blue lines represent Earth's magnetic field. As the solar wind comes towards Earth, it actually bends the magnetic field. So instead of being that even kind of magnetic field, when there's solar wind, it will kind of stretch the field out. And when the fields come together, so when the magnetic fields couple together, they funnel the solar gases towards the Earth's poles. So this green line represents the fusing of the sun's magnetic or electromagnetic pulse that's coming towards Earth and Earth's magnetic fields. And so we get this unusual, well, we have these smooth shapes here, but when they come together, we get this more unusual shape. And what happens is the gases, the coronal mass ejection from the sun, will now funnel down this new kind of formation shape. And the coronal mass ejections, the gases from the sun, will get trapped in the poles of Earth. These will get trapped up in these poles, and because this side of the Earth is sunny, the sun's on this side would be dark because it's on the opposite side of the sun. This would be called a daytime aurora at the poles. As these gases form at the poles, it will be a daytime aurora. But as the field passes Earth, they will start to kind of sling together from the backside, and as they connect, it'll create more of the solar coronal mass ejections will form on the backside of Earth, and this is called a nighttime aurora as these guys come from the back. So when they come directly on, that's the daytime aurora, and then when they sling from the back and come to this direction, that's a nighttime aurora. Regardless, these coronal mass ejections from the sun get trapped up here, and Earth's magnetic field traps them up here, and these are the northern and southern lights. And they make beautiful pictures. And so if you were going to go to see on vacation to see the northern lights or the southern lights, you might want to time it by looking at the sun cycles, those 11-year sunspot cycles, and try to go when there's more solar activity. When the solar cycle would be at a higher peak, you're more likely to see the auroras. A surprising amount of stars are actually paired or triplets. They're not alone, but when we look up in the sky, they just seem like one star. But in actuality, about a third of them are actually orbiting around another star, or even 3 stars orbiting together. The further a light source, the dimmer it becomes. The apparent magnitude is the brightness as perceived by the observer. So in this illustration below, we have 2 stars, A and B, and they appear to be the same level of brightness. But in reality, B is much dimmer than A, but B is also much closer than A. As A is further away, it looks dimmer. This is the idea of apparent magnitude. Apparent magnitude is based on a scale that was created by an ancient Greek astronomer, Hipparchus. And what he did is he looked up in the sky, in the stars, and he assigned the brightest star the value of 0. And then all the other stars got a number greater than 0, so the numbers increased from 0. That's how the scale works. What happened later, though, is telescopes got invented, and we found stars that were even brighter than the ones that were originally assigned the 0. And so those numbers had to become negative. So when you see a brightness scale, you'll see negative numbers and positive numbers. And it's important to note that the reason there's positives and negatives is because at the time the scale was created, 0 was the brightest. So that's why there's negative numbers in the scale of brightness. So absolute magnitude is the measure of how bright the star would be if they were all the same distance, which is 10 parsecs from Earth. So if we take that other example and put both stars equal distance from Earth, you would clearly see which one was brighter than the other one. It's the actual brightness of it. So for instance here, we have a star, and its apparent visual magnitude would be a measure of 3. But if you put it 10 parsecs away, the absolute magnitude is a measure of 0.8. So remember, the smaller the number, the brighter. So this is getting brighter as it gets closer. And this would be really how bright the star is. But what we see on Earth is 3 when you look up in a telescope. So we have to know the distance, and it's a little math formula that you're going to take the distance and you're going to take the apparent magnitude to calculate what the absolute magnitude would be. Here's a table of stellar brightness. I'm not going to ask you to memorize this table. I'll give you this table, but you need to know how to read it. For instance, let's take a look at the sun here. I might ask, from Earth, which star appears the brightest? And to figure that out, you would look at the smallest number, which happens to be the sun. Obviously, it's the brightest star we know of on Earth is the sun. And that's because it's the smallest number, negative 26.72. Then I might ask you the absolute magnitude. Which of these stars listed here is actually the faintest? Which one's the dimmest of all these stars? And in this case, you're looking at the larger number, which actually happens to also be Earth. The sun. The sun is the brightest as observed from Earth, but it's also the faintest when compared to these other stars here. And might ask other questions like that. You just need to know how to read it. Apparent is what we see from Earth. Absolute is what it really is. Larger the number, the fainter it is. Smaller the number, including negatives, the brighter it is. Reviewing back to what we talked about on the last lesson, we talked about temperature and color. Red is a long wavelength. It's a long wavelength and low energy. And blue is a shorter wavelength and higher energy. When we look at stars, the temperature of stars the color relates to its temperature. The coolest stars are red, and then as they get warmer, they turn orange, then yellow, then white, and then blue. The hottest stars are blue, the coolest stars are red. As the size of a star increases, it's increasing. The larger the star, the more atoms it has. The more atoms it has, the more mass it has, because mass is the atoms. It's the protons, neutrons, electrons. That's what creates the matter of something. And so the larger it is, the more massive it is. In general, we're going to talk about some exceptions later. So the greater the mass, the brighter the star, the hotter the star, and the faster it goes through its life cycle. So more mass, it's going to be brighter because there's more fusion. It's going to be bigger and there's more pressure. There's going to be more fusion, which will make the star brighter, which will also make the star hotter. And with more mass, it'll actually make it run through its cycle faster. To give you an idea on how big some stars can be, this is Betelgeuse, which is one of the larger stars that we've observed. And compared to the sun, it is enormous. This is actually a giant star. This is somewhat of an unusual situation, a giant star. But you can see the sun compared to Betelgeuse, in this scale, it looks like Earth compared to the sun. So very, very, very lopsided. On the other side of the scale, our sun would be this picture here, this enormous picture here. This is the sun, and this would be how big Earth is compared to it. This is a small star. Sirius B is a dwarf star, which is just slightly bigger than Earth. So our star, the sun, is actually not the biggest, it's not the smallest, it's kind of an average star. And if you take a look here, this is called an HR diagram. If you take a look here, what I'm talking about is this line right here. You really got to pay attention to this line right here. This is the most important part. This is the trend I'm talking about. 85% to 90% of the stars will fall on this line. So this is the trend we're talking about. This big blobs over here that's catching your eye, these big stars, I know it's catching your eye and it pulls you off of that. Don't focus on those. We're focusing on this over here. We'll talk about these guys off the line in a moment. So the bigger the star, the hotter it is. So as we go on the x-axis to the left, it's hot and blue. You should note the bigger it is, the more blue it's going to be and the hotter it's going to be. And at the y-axis, the brighter it's going to be. So big star, more mass, it's going to be bright, it's going to be blue, and it's going to be hot. As the star gets smaller, notice the size of these, diameter of these stars on this cycle right here. This is called main sequence right away. 85 to 90% of the stars fall on the main sequence line, this trend. So as it gets a little smaller, the stars are white, they're not as bright, and they're not as hot. And then we come down, we get stars that are yellow and orange. Our sun is right in this area here. It's right in the middle. And then finally, we get really small stars that are faint, cool, and red. The anomalies are the giants. Giant stars are very bright, but they're not very hot. So they're cool and bright, and they're huge. These are giants. And white dwarfs are very hot. They're hot and they're white, but they're rather faint and they're very small. These guys here are the anomalies. They don't happen as much. Like I said, 85 to 90% of the stars will follow this trend here. The material that's not part of a star, not part of planets, material that's floating out in space is called interstellar medium. Interstellar medium is composed of dust, ice, elements from star explosions. If there's enough interstellar medium, gravitational forces will cause them to condense together and make cloud formations. When you can see the interstellar medium, this is called a nebula. Stars form, they start from nebulas. The gravity of this interstellar medium towards itself will start to make this dense cloud, which is a nebula. And the cloud will start to come together, and as it starts forcing together, it starts spinning as it comes closer and closer together, almost like water going down a drain. It's going and coming together, and it's putting more and more and more pressure, and it's spinning like a disc. Eventually, it starts getting so hot, the pressure and the friction on the center, it'll start to get warm and hot and glow. But this is not quite a normal star yet. This is what we call a protostar. As we can see this bright, hot center of the nebula, this protostar, pressure builds up and gas can burst out at 90-degree angles from the disk. This is a protostar. It's different than a main sequence star because at this point here it's getting pressure and it's getting hot, but it's not undergoing nuclear fusion yet. So the birth of a main sequence star happens after the protostar. If there's enough material, interstellar medium, for this nebula to be big enough, it'll put enough pressure on there that gravity will cause hydrogen to fuse into helium, releasing a massive amount of energy. In other words, it's undergoing nuclear reactions at this point. Once it starts undergoing nuclear reactions of fusion of hydrogen to helium, it is now a main sequence star. All right, so let's review where we are right now in a star life cycle. A nebula is the gases. They come together by the gravity of the matter of the gases and create a nebula. The nebula then pushes in further and further together, and it starts to make a hot, dense core, which is the protostar. And once the protostar starts to undergo nuclear fusion, then it becomes a main sequence star. Our star, the sun, is in this stage right now. The next stage our star is going to do is become a red giant. The nebula turns into a protostar, which then turns into a main sequence star, and there's so much material, there's so much gravity, it's pushing in, that it starts to undergo fusion, which starts to explode and push out. And it's actually, the gravity counters the fusion in main sequence stars, keeping it stable. A star will spend most of its life in this stage, where the hydrogen is fusing into helium, and that's offsetting the massive pressure, the massive gravity of trying to crush it down. But eventually, that hydrogen will run out. And when that hydrogen runs out, when all the hydrogen turns into fusion and turns into helium, the fusion's gone, and gravity is all you have, and the gravity crushes this down into a very, very small diameter. It crushes it down to much more dense. And the outer atmosphere, the photosphere of the star, expands further out. So it crushes down in the middle, but the atmosphere expands out. So you got this really hot center, and it turns enormous. It's so enormous that it's said that when our sun turns into a red giant, that it'll expand so far that it'll engulf Mercury, it will engulf Venus, and it will get right to about the distance of Earth. It might swallow Earth, it might not swallow Earth, but it's going to expand an enormous, enormous amount of size. Now, at this point, the core crushes in, and now there's even more density, more pressure than there was before because it's in a smaller area, and now the helium will start to fuse. This is a red giant. In main sequence stars, it's producing hydrogen and helium, but in red giants, the helium is now fusing into larger elements as large as carbon and oxygen. This is being fused in the core of a red giant. As it expands out, the outer layer isn't as close, and so it cools down. And that's why red giants are very large and also cooler. And they're also very, very bright because it just came from that stage of a star. So it's bright and it's cool and it's moving out like that. So the next stage is after all of the helium is turned into things like carbon and oxygen. We'll say oxygen, that's the bigger of the elements. So once it's fused to the biggest elements it can, and that runs out, the next stage for a red giant is to become a planetary nebula. The outer layers of the red giant will expand and expand and expand. As they expand, they get further away from the dense core. Gravity has less of effect of it, and so it just drifts off into space until eventually this red giant just turns into a huge cloud around the bright core that it once was surrounded by. This is called a planetary nebula. It looks like a nebula with a faint hot star in the middle of it. The nebula from a planetary nebula, the interstellar material that came off of it, can then float off into space, mix with other material in space, form another nebula, and then go start the life cycle again. But what's left in the center, that hot center, becomes a white dwarf. A white dwarf is just the core of a red giant. As the red giant layers peel off and all you have is that hot core in the center, that is the white dwarf. That's why white dwarfs are very small and very hot. So they're very hot, they're very small, but they're not very bright. And so in a white dwarf, fusion is over. This is the remains of the red giant that's basically died. So the white dwarf will continue to cool over time. It is not undergoing any fusion anymore. There's no more nuclear reaction in white dwarfs. They're very dense and they're very hot, but they're cooling down over millions of years. Eventually they'll cool to the point that the white dwarf will be considered a black dwarf. The white dwarf eventually cools off and forms a black dwarf. It's no longer hot. It's basically a very dense rock that's floating out there. It's going to have the same large gravitational field as it did when it was a main sequence star, but now it's much, much smaller, much, much denser. Okay, let's go again, but now we have a very large nebula. It makes a larger protostar, and so now we're talking about a larger main sequence star. If you look at your HR diagram that we talked about earlier, we're talking about the large stars, these larger main sequence stars that are blue and white, these bigger ones. So not like our sun, the yellow and orange ones. So the blue and white stars, what happens to them? So the same thing, it's a main sequence star. It's going to turn its hydrogen into helium under nuclear fusion. And then when the hydrogen runs out and it's converted everything into helium, then the outer core, the outer layers will expand and you'll start to get a very large giant again. But this is called a red supergiant. Yeah, they put the word super on there. And there's more than just the fact that it's very large. In a supergiant, because the core has even more mass than a giant, the giant will only convert things up to oxygen. With a red supergiant, it allows larger elements all the way up to iron to be formed. So in red supergiants, all the elements up to iron will be formed in red supergiants. Eventually, it'll run out of atoms to fuse. It'll stop once the core becomes iron. So red supergiants will get an iron core and there won't be any fusion left over. And at that point, the red giant will move into the next stage, which is a supernova. So it burns up all the iron. It burns up everything till it's a core. It fuses everything till it's a core. And then because the core is so dense and so massive, the outer shell, unlike a red giant, in a super red giant, it just expands into a nebula. On a super red giant, once the fusion's over, that's kind of holding that atmosphere back, that's holding the photosphere or the gases, the outer layers of the star back. Once it stops the fusion and it gets this iron core, then these outer layers come crashing back into the core. So once the fusion stops, the outer layers collapse into the core, then they rebound in an enormous explosion. All the elements heavier than iron, such as gold, silver, platinum, were fused inside a supernova at the moment of explosion. So everything comes crashing in and bam, all this pressure, now we start to get all the elements bigger than iron forming. So and then they hit and they explode and they go all over the universe. They shoot off all these heavier particles, all these heavier elements. So those heavy elements can then form into gases, which can find gravity with other things and create another nebula. This is what happened with our star, the sun. It had to have been a supernova, and that was part of, and so these heavier things, such as, like we said, in their gold, uranium, plutonium, platinum, all these heavier elements formed another nebula, which formed our sun. Because when our sun formed, some of those elements didn't go into the core of the sun, but they went into other rings that cycled together and formed gravity, formed them together, formed planets. And that's why our planet has things on it like gold. If you've got gold, that's literally something that was forged in a supernova. Now, once the supernova, boom, everything explodes, what's left of that core? What's left of that core is a neutron star. So neutron star is so dense. Now there's no more nuclear fusion and there's so much material that it all collapses in on itself. And we talked about it before in chemistry that an atom is mostly empty space. We learned this from Rutherford's experiment with gold foil, that it's a very small nucleus and it's an electron cloud. And it's the electron clouds that repel the electron clouds of other elements. That's the resistance that we feel. Like my two hands, the nuclei aren't touching each other. It's actually mostly empty space. It's the electron clouds that are resisting each other. But there's so much gravity, so much pressure, so much density in this core, and there's no fusion that's releasing energy to resist it, that all these electrons crash into the nucleus. They crash into the protons, turning all the protons into neutrons. And then they stack together. So if you don't have these big empty electron shells, everything crushes together in a very, very small, tight space. An analogy I heard, if you took the Empire State Building and you took all the atoms in the Empire State Building and you crushed them all into just neutrons, the whole Empire State Building would occupy the space of a grain of rice. However, it would still have all the neutrons and all the mass of the Empire State Building. So imagine the mass of an Empire State Building as a grain of rice. Another thing I heard is if you took a teaspoon of neutrons, take a teaspoon of a neutron star, it would weigh 1 billion tons. So it's extremely dense, and it crushes down into a very, very small size. When we think about stars, they're enormous, much bigger than Earth, but when it becomes a neutron star, and I'm talking about large main sequence stars, like the blue ones and the white ones that are bigger than our sun, when they crushes down into become a neutron star, their size is, the diameter is only 20 kilometers, which is like 12.4 miles. So it's like a small city, the neutron star, except it's going to have a gravitational field stronger than that of our sun. In other words, our sun would orbit around this thing that's only like 20 kilometers in diameter. It's really, really dense. If there's even more material, instead of making a neutron star, it can form a black hole. A black hole is just an extremely large neutron star. It's just a whole lot of neutrons. In fact, it's not a hole at all. It's the most dense matter you can have in the universe. So it's crushing all the protons and electrons together to make neutrons, and it's got such a strong gravitational field that a black hole could actually suck in a close by star. And this is a nice illustration of a star being pulled into a black hole. And as it gets pulled into the black hole, its atoms are going to get crushed into neutrons, which makes the black hole will become bigger and bigger and bigger. There's theories that black holes collide into each other and make even larger black holes. So a black hole can start from a large main sequence star, but then they can grow and grow and grow in size. It's believed that the Milky Way, our galaxy, is all of our stars, our sun, and all the billions of stars in the Milky Way are orbiting around an enormous black hole in the center of the Milky Way. So, black hole, the difference between a black hole and a neutron star is it gets to a level of mass that not even light can escape a black hole. That's the difference. That's what I would say is the dividing line on how big is something become a black hole versus a neutron star. So, in sum, you should be able to figure out where the different elements are made throughout a star life cycle, because all the elements that make us who we are in our life came from stars. So first of all, we have a nebula. That's interstellar material. That interstellar material will come crashing together, creating a protostar with a lot of friction. The protostar will then start to undergo nuclear fusion, where the hydrogen is formed, and the hydrogen will start fusing into helium. So hydrogen and helium will be formed in the main sequence stage, which will be the majority of the life of the star. It's the stable stage also. Once all the hydrogen runs out and it's just helium, it will become a red giant. The outer layer will expand and cool, making it red, and then the star will collapse in, get even denser, and because it's even denser, now you can start fusing the helium. The helium will start to fuse to make things as large as oxygen, but eventually that will run out. When that runs out, the outer layer of the red giant will drift off and drift off and drift off until it just becomes a nebula with a faint, hot, white star in the center, which is a white dwarf. After all the nebula is gone, it's just called a white dwarf. As it's surrounded by the nebula, it's called a planetary nebula. The white dwarf is no longer undergoing any nuclear fusion. It's not undergoing any energy creation, and so it's going to cool and cool and cool, and then eventually it turns into a black dwarf, which is the final stage of that star. If it's a larger nebula, it creates a larger photostar, makes a larger main sequence star. These main sequence stars are going to be larger. They're going to be blue and white. When it runs out of, it'll create hydrogen and helium. When it runs out of the hydrogen and it just has a helium core, it condenses together. It makes a red supergiant. Because this core is even larger, it can then make elements as large as iron. Once it creates an iron core, there's no more fusion, and then the outer shell comes flying in and rebounds off the core, making a huge explosion, making a supernova explosion. And during that stage, all elements larger than iron are formed. So this is where we get the large elements. Everything else on your periodic table gets formed through the supernova. And then that explodes out. What's left over is a very, very dense center, so dense that the protons and the electrons combine, and it's just made up entirely of neutrons. It's packed in tight, just neutrons, extremely, extremely small and extremely dense. And if it was enough of them, or even neutron stars combining together, once it gets large enough, it becomes a black hole. A black hole, light can't even escape it, so it looks like a dark black hole in space. That is our star life cycle. I hope you're ready for the quiz. If you have any questions, let me know, and good luck.